Okay, so this video is to discuss 9.4 sampling distributions for proportions. So this is a whole new world for us. We have been working with quantitative data and calculating means and working with distributions of means. But we also want to talk about qualitative data. And when we start with qualitative data, the population is of individual colors or individual categories is not directly able to calculate a probability for. We need sampling distributions where we essentially start working with portions of different categories. So P, lowercase p, is our symbol for population proportion, while this little guy, P with a hat on it, it's called P hat. P hat is called the symbol for the sample proportion. And all a proportion is the part over a whole. It's a fraction, just like relative frequency, just like probability, just another way of talking about the part over the whole. So X represents the category that we're focused on for the proportion. That would be the part. And N, as always, is our sample size. So that's all the count of all items in the data set are all categories. So for example, if you take a look at the population down here, we have some balls, some blue ones and some red ones. If we let X represent the red balls, then the part would be 3. N represents the total number, the count of balls, which if you count these up, you'll see that there are 8 total balls. So if we wanted the proportion of red balls in the sample, we would put 3 over 8 and come up with a sample proportion of 0.375. So introducing proportions, now we are going to be looking at a population that is of categories such as M&Ms and their colors or anything categorical. And we will be using the central limit theorem in order to find probabilities of a particular proportion, and the probability that it would be greater than, less than, differs more, differs less than. So I just wanted to show you what the central limit theorem formula looks like. So recall with the means, the central limit theorem, once passed with the criteria, stated that the mean will always be at the center and that won't change when we transform into a sampling distribution. The same thing is true for proportions. So whatever the population proportion is of the original population is going to be the same proportion of the sampling distribution. As for the standard deviation, there is no standard deviation of the population as we're working with categories. So there's no way to calculate a standard deviation for the population, but there is a way to calculate the standard deviation of the sample proportion, also known as a standard error for proportions. And that will be seen by this formula here, where we take the big square root of the population proportion times 1 minus the population proportion, also known as Q, divided by the sample size, all under the square root that time. Now, what is the criteria for the central limit theorem? The central limit theorem has us passing these criteria right here. Okay, so instead of the sample size needing to be at least 30, very simple criteria to pass for the means, we have a little bit extra work to do to pass for the proportions. So we would take the sample size and multiply it by the population proportion and make sure that that is at least 10, and which means you have to do both and you have to pass both for the central limit theorem to be valid. You have to multiply n times 1 minus p, also known as q, so n times q also needs to break the threshold of 10, okay, or be equal to 10. Okay, so we have to pass both of these in order to say that this formula here is a valid formula and therefore our probabilities are accurate. Okay, so let me get out of the learn mode and let's enter into the practice mode and let's take a look at some examples and do them together. So suppose we have 50% of the students in a university are baseball players. If a sample of 853 students is selected, what is the probability that a sample proportion of baseball players will be greater than 46%? Okay, first thing we need to know in the world of proportions is that we will never use the percent form. We will always be translating these into decimal form. So recall, to change from percent to decimal, you move your decimal place over 2 points to the left. So right now the decimal place is right after the 0. When I move it 2 places to the left, the proportion would be 0.5. All right, let's first make sure we pass the central limit theorem before we get too far into this and realize that our formulas are not even valid. So we have a sample size of 853. So let me make note of that, 853. And we have a population proportion of 0.5, representing 50%. Okay, so let me go over here to Rguroo and let me pull up just the basic calculator because I just need to do that criteria for the central limit theorem. And recall, it is the sample proportion, or the population proportion, excuse me, times the sample size, 853. And I have to make sure this number is at least 10. Check, that works. Okay, I also need to do 1 minus the proportion. Okay, in this case, 1 minus 0.5 is still 0.5. So this is also going to pass because it's the same calculation, but that's not always the case. So it only works with the 0.5. Either way, both of these have broke the threshold of 10, and I have passed the central limit theorem, which means that the population proportion of 0.5 is also the average of the p-hats, or the sample proportions in my sampling distribution, will be at 0.5. And I have to calculate my standard error. So my standard error was that formula, the big square root. Let's create a division sign underneath a fraction. In my numerator, it was the population proportion of 0.5. And I multiply that by 1 minus the population proportion. In this case, also happens to be 0.5, but I want you to see the formula. And then we divide by the sample size. Okay, so this is what the formula looks like for the standard error of proportions, or it could be called the standard deviation for the sampling distribution of proportions. So I'm going to need to copy and paste this so I can put it into my standard deviation box in my continuous probability calculator. So I'm going to head over here to the probability simulation area, drop down my probability menu, and select the continuous probability calculator. Okay, now this calculator does not switch back and forth from proportions and means. You would just set your mean to your population proportion, which was 0.5. And I'm going to paste in my sample, my standard error of proportions. Again, I like to scroll to the front to make sure that I copied and pasted properly. Just double check that number looks the same. Good. And now let's look over at the problem. What were they asking me to do again? They're asking me to find the probability. So my mode on my calculator should be the arrow pointing to probability, that the proportion would be greater than 0.46. Again, I'm translating this percentage into decimal form. So greater than is going to be an above. And I'm going to put my proportion of 0.46. And when I hit my eyeball, I find out that the probability that the proportion would be greater than 0.46 is about a 99% chance. So that's a very likely chance of occurring. Right, let's take a look at another one. Let's see if we have a differs problem like we were talking about. Here we go. In the means problem, you're also going to have these differ from and then greater than or less than. Recall from the means video of 9.3 that differs is always separated from the less than or greater than or more than, however they word it. So you really have to read the whole sentence in order to make sure you're selecting the correct thing in Rguroo. When you differs more than, you are exceeding the upper and lower limit, or an outside problem. And when you differs less than, you are contained between the upper and lower limits, which is a between problem. Okay, so this problem states a direct mail company wishes to estimate the proportion of people on a large mailing list that will purchase a product. Suppose the true proportion is 0.04. So that's another way of saying the population proportion. If 259 are sampled, what is the probability that the sample proportion will differ from the population proportion by less than 0.03? First step is to pass a central limit theorem. So we're going to use the 0.04 and our sample size of 259 in order to see if the central limit theorem can even be used in this problem. So I'm going to head over to my calculator and I am going to put in my proportion of 0.04 and multiply that by the sample size of 259. Woo, that barely made it. Okay, 10.36. I needed to at least be 10. Okay, it could be more, but it had to be at least 10, and I'm barely 10. So far, so good. So then I take 259 and I'm going to multiply by 1 minus 0.04 because remember, you have to pass both. This one passes with flying colors. So I have successfully passed a central limit theorem, and that means that the average of the proportions from the sampling distribution is going to be equal to the population proportion of 0.04. So in my calculator, I'm going to change my mean to 0.04. And to calculate my standard error, I am going to put a big square root with a fraction underneath. To do that, you just hit your division sign. The numerator is going to be 0.04 multiplied by 1 minus 0.04. And my denominator is going to be my sample size, 259. I am then going to copy and paste this standard error for this sampling distribution of proportions. You can copy on your keyboard by using Control-C if you're on a PC and Command-C if you're on a Mac. I am going to double click this box so I highlight the whole number that's already in there, delete out the number, and you'll use Control-V on a PC or Command-V on a Mac to paste your new standard deviation in. Again, I like to scroll to the beginning to double check that it remotely resembles what I was trying to put in there, and it looks good. Okay. Now this problem asked us to differ less than, okay, again, that means within the limits, which is a between problem. And we will have to calculate our limits by taking our mean of 0.04 and adding and subtracting the differ amount that they give, which is right here, our 0.03. Okay, so first always select your drop-down selection from this window because as you change selections, it will clear out whatever you've typed in, which can be a little annoying. I am going to, in my calculator, take 0.04 and subtract 0.03 to get 0.01 as my lower limit. And then I will take my 0.04 and add my 0.03 differ amount to get my upper limit of 0.07. Okay, so now I have my upper and lower limit, and because I want to differ less than the differ amount of 0.03, I want to be between these values, and I click my eyeball for my probability. So there's approximately a 99% chance that the proportion for whatever we're working with, what were we working with? Oh, that the proportion of people on a large mailing list will be between 1% and 7%, or 0.01 and 0.07. All right, let's try one more together. Let's see, this is a differ less than. Let's do a differ more than. Here we go. Goofy's fast food center wishes to estimate the proportion of people in its city that will purchase its products. Suppose the true proportion, again, the population proportion is 0.07. If 324 are sampled, what is the probability that the sample proportion will differ from the population proportion by more than 0.04? So things that we need is that the population proportion is set at 0.07. We need our sample size of 324, and we're going to use this so that we can make sure that our central limit theorem criteria has passed so that everything we do from there on out is valid and accurate. So coming over here to my calculator, I am going to use the criteria of the central limit theorem. by multiplying my sample size of 324 by the population proportion of 0.07. I check over here. I check that the number is at least 10. It's good to go. So then I'll do the other part of the central limit theorem, which says take your sample size and multiply by 1 minus the population proportion, and also meets the criteria of at least 10. Okay, so now that I have verified the central limit theorem is valid, I know that the average of the sample proportions, my mu sub p hat, is equal to the population proportion of 0.07. So in my continuous probability calculator, I'll set my mean to 0.07. I also now need to calculate the standard deviation for the sampling distribution of proportions, or the standard error for proportions, whichever way you want to label it. And that's a big square root with a fraction underneath, where my numerator is the population proportion times 1 minus the population proportion. And my denominator is the sample size of 324. I'll then highlight my answer, copy. Double click to highlight this whole thing. Notice that if I hover my mouse, it does pop up in a yellow box, the whole number. Delete and paste. I'm going to scroll onto the front and make sure it pasted correctly. It has. This problem said differ more than. Okay, so that means I need to differ more than the upper and lower limit, which is an outside problem. I'm going to need to calculate my lower limits and my upper limits. So I'm going to come right back here to my calculator, and I am going to take my mean, which is the population proportion of 0.07, and I'm going to subtract the differ amount of 0.04. So my lower limit is 0.03. I am then going to take my mean and add that differ amount to get my upper limit. And that gives me 0.11. That's going to come over here in the upper limit. We're going to select our eyeball so that we can see that it is very unlikely for this to occur. So again, this problem is talking about the proportion of people in its city that will purchase its products. And we can say that there is a less than 1% chance that less than 3% of the population will buy these products. It's also a less than 1% chance that more than 11% of people will buy these products. Okay, so that's what an outside problem is saying. It's outside these limits. All right, I hope this was helpful for your 9.4 homework.